Okay, now we're live. All right, now let me try to answer your question. Why don't you ask your question one more time while I'm no longer thinking? No. Okay. Did I answer your question, or did I just completely blow you off? Are you sure? Okay, because I'm pretty sure I trailed off there mid-thought. Okay. I remember what I was saying. Yes, it's combined between the autonomic nervous system, localized regulation, plus hormones. There. All right. So there are three basic renal processes. All right. In essence, what we're going to be dealing with are glomerular filtration, tubular reabsorption, tubular secretion. We're going to probably get through the first two today, and then we're going to deal with tubular secretion on the end. Now, the big picture of all this is you have to think like this. Glomerular filtration basically is no. Much better. You were nervous, weren't you? All right. 20% of the plasma in your body is going to be filtered through the glomerulus. That accounts to about 125 mils per minute, or about 180 liters per day. Now let's do some simple math here. 125 mils is about a third of a can of soda per minute. How often do you go to the bathroom? No, just think. On average, how often do you go to the bathroom? 3, 4 times a day? All right. Harder question. How much do you actually go? How much do you pee out, do you think? If you had to guess. I mean, you can think back when you went to the doctor last time and did the urinalysis and you had to sit there and hold the cup and balance yourself or whatever. You know, and you're sitting there going, they give you a cup that's like a shot glass. No. Think about a normal bathroom break. How much you'd actually go to the restroom. Half a liter. You're about right. About 500 mils. All right? About right. So if we are filtering 125 mils per minute, how often would you be going to the bathroom? Simple word problem. Every 4 minutes. That doesn't add up. Which would make sense, of course, right? Because if you were filtering 180 liters of blood per day, I mean, you'd basically be one desiccated little corpse, wouldn't you? I mean, you only have 5.5 liters of blood. So, I mean, just think how quick. So what that means is that everything that's filtered doesn't become urine. So even though we're filtering stuff, and that's happening here at the level of the glomerulus and Bowman's capsule, that's not the only process to make urine. Tubular reabsorption basically says, you know what? Filtration is a non-specific act. I mean, it's specific in the sense that if you're too big to be filtered, you're not going to be filtered, but anything else beyond that is going to go through. Right?
So it's in the first in a big seed.
Exactly. And let's think. I mean, how many of you guys ate today? I mean, you went out. Did you go spend money to buy food? No? Good for you. For those of you who didn't spend money like me, I mean, you feel like a fool, right? And you spent good money to get glucose into your body, right? I mean, you went down. I mean, like me, I went to Taco Bell. I mean, if you were smart, you went over and went to the pharmacy school and took part of their wonderful international cuisine. You guys didn't see this, did you?
You guys like right into the right?
Yeah. I mean, they had, from some of the best restaurants in town. They were serving all different types of international fare for like $5, $10. I can't remember what the price was. Yeah, of course. I mean, I consider California international. You know, but what happens is you can think about this. You just spent good money getting glucose into your body. You spent good energy getting down to the UC Underground to get that food. And then if your glucose is too small to not stay in the blood, it's going right into the urine. And the next thing you know is you're peeing out money, time, and energy. Is that right? I mean, is that about right? Is that a waste? I mean, your mom would think so. I mean, my mom would grab me by the ear and say, So, your body thinks so too. And so it says, you know what? No. If you're going to spend that much energy getting food and energy into your body, we're going to hold on to that. And so what we do is we put materials that your body wants back into the body through the process of reabsorption. And so at the end of the day, you end up making about a mil of urine per minute. So for every 125 mils you filter, you return about 124 mils back to your body through the process of reabsorption. Now, does this make more sense? A mil per minute, that means about 60 mils per hour. How often do you go to the bathroom? Every hour? I think you need to go see a urologist. You know? You basically make about 1.5 liters of urine per day, which translates into what you guys told me. I go to the bathroom about 3 or 4 times a day. Sounds about right. Okay? The third process is the process of tubular secretion. And what we're doing with tubular secretion is we're taking materials and removing them directly from the blood. All right? In other words, what we have is we have molecules, carriers, that can selectively find materials that the body doesn't want, grab them in the blood, and transport them across into the tubule. And this is a way we get rid of materials faster than we normally would through the process of filtration. So after all these 3 things, and it shows you here in this nice little thing, this little drawing, it says, look, here is where all these processes are taking place. And you can see that each different region has different responses. We're going to deal with all of these in just a moment. Is that at the end of all of this, you've now created a very unique and specialized fluid that basically consists of the things that your body doesn't want. Make sense? That's why we're not peeing out glucose, because your body wants it. Now we're going to start with filtration. All right. Now, remember what we said, is that it's not going to be all the blood. If you pushed all the blood through as a filtrate, then basically all the fluid would go this direction, and then all you'd be stuck with is a bunch of red blood cells. And that's not going to do you any good. So you're only going to be filtering out a small portion of the plasma to make sure that you still have a liquid component to the blood. All right? So about 20% of the volume of the blood is going to be filtered through. About 19% of it is going to be returned back through the process of reabsorption. Now, in order for filtration to take place, you actually have to pass through 3 separate membranes. Now, the first membrane is going to be the glomerular capillary wall, so the endothelium. And remember what we said is that we have a capillary, so we have endothelial cells. When we looked at capillaries before, we said that they had tight junctions that were slightly leaky, so that, you can think of it like this, like I can pass between my fingers, right? Because if I'm small enough, I can do that. Well, here, what we have is we're a little bit more permeable, just a little bit. Dang it. Yes. 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 I better be getting that right. It's been one of those days. All right. And so here you can see that in our little cartoon here is that we have this space, this gap in between capillaries. So it allows bigger materials to pass through than what we'd see in a normal and regular capillary. So because you're 100 times more permeable, more fluid, and the stuff, the solutes that's small enough to pass through with that water through bulk flow is going to pass through. But underlying the capillaries are a basement membrane. And so we're basically talking about a kind of molecular sieve. Basically, it's collagen and other glycoproteins that are basically overlying each other. And so it kind of acts as a meshwork or sieve to really kind of prevent those larger molecules from escaping through. And then what they do is they kind of work their way through that, and then on the other side you have the inner wall of Bowman's capsule. Remember, it starts on this side and goes back around this way. And so what we have here, the cells that make up this wall, are called the podocytes, and they're called podocytes, foot cells, because the way they're structured, you can see their little drawing here, it has these little tiny feet. And they wrap themselves around the endothelium, and they interdigit, or they have interdigits like so. And so it acts as a sieve on the other side. And so this is kind of what it looks like. You can see that you'd pass through from the capillary through that basement membrane and then through the slits between the podocytes. And that's how filtration takes place, basically through these three layers. If you're small enough to get through all of this, you're going to be filtered. Ah, yes, forces. I know how much you guys love forces. Three forces are involved in the process of filtration. You'll notice that these have very similar words or terms that you've seen before. All right, we have the glomerular capillary blood pressure, and this is the major driving force. It's just basically blood pressure that's driving fluid down the path of least resistance. All right. Now, one of the reasons that this happens is because our afferent arteriole, in terms of its diameter, is bigger than the efferent arteriole's diameter. And so what happens is when the blood goes into the capillary and starts circulating around, it doesn't go out this direction quite as fast as it entered in. And so you end up with this backflow, this pressure building up in the glomerulus, and so that fluid is going to look for the path of least resistance. Some of it goes out through the efferent arteriole, some of them go through those little tiny slits. The pressure here is about 55 millimeters of mercury. Now, as you filter out that fluid, you're leaving behind plasma proteins. No plasma proteins in the filtrate, plasma proteins in the plasma. So now you have a colloid osmotic pressure that's going to draw water back into the capillaries. So water comes back. All right? Sorry. That's what this one represents. So water moves back into the capillary. So it's a negative force. All right? The third type is just another hydrostatic pressure. Now, I'm going to erase all the ink on this slide real quick just so you can see what I'm talking about. What we have here is we have a very finite space. All right? And we fill up this very finite space with fluid very quickly. Now, where does that fluid want to go? You can follow the arrows. It just wants to keep going down the tube, right? But just like anything, when you have a small tube and you have a lot of fluid entering into that tube, are things going to slow down? Yeah. And so basically, as the fluid backs up because of the pressure inside that tube, it's going to become an opposing force to the fluid that's moving in. I always use this example, but no one ever appreciates it. When you were a kid and you took a hose and it was turned on and you stuck it in your mouth, right? I mean, your mouth fills up really, really quickly with water. Where does the water want to go? Whichever way it can, right? Path of least resistance. Now, if you're crazy, you're just going to open up your throat and the water's going to go down into your stomach until it fills up there. But usually that's not what happens. Usually you sit there and then it starts coming out around the hose, maybe up and out your nose, stuff like that, right? But it's something that you already know what it does. It goes down the path of least resistance. And that's really what it is that your mouth fills up with that water, and so the water's going, where do I go? In the hose, it goes, where do I go? Well, it's going to start opposing the movement of that water. It's just that it so happens that you don't have the strength to force the water back down the hose. That's why it comes out your nose. Not a great example, was it? I don't know, maybe. Anyway, if you look at all of these pressures, you basically have a negative pressure, and a positive pressure, and all we got to do is compare these three or put them up together, sum them up together, and it'll tell us which direction we're going to see filtration. And so our glomerular capillary pressure is 55, the colloid pressure is minus 30, the fluid pressure is minus 15, sum them up together, and you get about 10 millimeters of mercury. And so that's our net filtration pressure. And so what we have is we have a positive pressure that drives fluid into Bowman's capsule from the glomerulus. We refer to this as the net filtration pressure. So it's a little bit easier than the bulk flow because we don't have to deal with that one that doesn't exist. But does that make sense? Now, the rate of filtration into Bowman's capsule is referred to as the glomerular filtration rate. It's going to be dependent upon that net filtration pressure, which should make sense. If I increase the net filtration pressure, is that going to drive more fluid into the Bowman's capsule? Yeah. And so if I'm driving more fluid, that means the rate has gone up. And then if I decrease the pressure, is that going to drive the rate down? Yeah. Okay, so you got that. It's also dependent upon the filtration coefficient, which we're not going to worry about. So all we got to do, if we want to change the glomerular filtration rate, we can change that capillary pressure. And how do we do that? Simply put, we can do it intrinsically, meaning we auto-regulate at the glomerulus, or extrinsically via sympathetic regulation. Have we learned anything new yet? No. Don't you love when we integrate information? Uh-huh. I will tell you. Autoregulation, simply put, is where the vessels themselves are going to be responsible for trying to maintain constant flow. When the pressure increases inside the vessel basically says, no, I want to reduce it down. I want to keep that flow constant. And that's in essence what the muscles do surrounding the vessels. They try to maintain constant glomerular, or basically constant flow with respect to a range of blood pressure. Now notice what this range is. It's pretty large, 80 to 100 millimeters of mercury. I mean, that's pretty wide range. But the idea here is just think about what you do during the course of the day. I mean, most of you throughout the course of the day sit in chairs doing pretty much nothing. But then once you leave campus, that's when you become wild people and you start running around like a bunch of wild people and start doing things like sports and getting in cars and yelling at people and cutting me off with your loud boom boom music. All right, but I mean, let me. Well, go ahead and ask a question.
I was going to say, like, I mean, the normal range of activity, that capillary blood pressure covers everything from eating a whole bag of salty laced potato chips to running 3 miles without drinking Gatorade.
I would think of it more along these lines. Well, yeah, I mean, if you're sitting in a chair and doing nothing, then your pressure is going to go up and down. But think about this: in a couple minutes, about 35, well, probably 30 minutes from now, you're going to all stand up. What's going to happen to your blood pressure when you stand up? It's going to drop, and what's your body going to want to do? Bring it right back up. And so what you're looking at here is basically 2 major changes in your blood pressure in a very, very small amount of period of time, right? You know, it initially drops, so you can imagine your peripheral blood pressure drops really, really low, maybe even into a range down here. And then when you bring it back up, you may be bringing it up here. And so the job of autoregulation is to try to keep the blood pressure inside the afferent arteriole, inside the glomerulus, within this very tight range. And so it's going to respond as the pressure is dropping. It's going to say, wait, no, we're not going to allow this drop to occur. We're going to constrict and increase the pressure so that we can increase the flow rate.
So it kind of tries to insulate the kidneys and any other outside changes.
Go even smaller. It's not just the kidney. It's that specific nephron. It's very local. So you can have one nephron doing one thing, and you have a nephron next to it doing something else entirely. Kind of cool. There you go. Now this does this through myogenic activity, which we've discussed. This is basically the cells there, and we also do it through a process called tubuloglomerular feedback. Now, myogenic activity, we've seen this, and I've just thrown this up here. It's really, really simple. Here we have our normal system. There's a glomerular filtration rate. You can see there's your renal blood flow. You can see that there's a certain degree of resistance and a certain degree of pressure within the afferent arteriole. We don't even have numbers up there. We just know that this exists because, well, I saw what you guys did on my exam. I'm glowering. When blood pressure increases, that's going to increase the glomerular filtration rate, right? And we already said that. Filtration rate is dependent upon pressure. If the pressure goes up, filtration rate goes up. So we don't want the filtration rate to go up. We want it to stay constant. So what we're going to do is we're going to increase resistance in the afferent arteriole, which is going to reduce blood flow into the glomerulus, which reduces flow rate. That makes sense? And then the converse is true. When your blood pressure decreases, you can do two things. And this example shows you I'm going to increase resistance here in the efferent arteriole, which causes blood to accumulate in the glomerulus, which increases the flow rate. But you can also do it here. What would you do here in the afferent arteriole? You dilate. More blood goes in, you increase the flow rate. So you see, this is myogenic activity, just in response to localized blood pressure at the level of the afferent arteriole. Kind of simple? I mean, it shouldn't be scaring you at this point because this is stuff that you've already learned. We're just now applying it. This is the stuff that gets wonky. Well, not really wonky. Tubuloglomerular feedback. Huh. Here we are. What's that structure called? How'd you remember? Exactly. It's the juxtamedullary apparatus. Or, sorry, juxtaglomerular apparatus. You can see I'd be the one on the bottom end of that curve. All right. Now, what this structure does, remember, this is the tube. And the filtrate is moving through the tube. Right? It's really a tubule, but it's moving through the tube. And you have cells within that tube that are responsible, called macula densa cells, that are sitting there monitoring the sodium chloride levels inside the filtrate. Now remember, the liquid inside the tubule is called the filtrate. We filtered it, it's why it's called the filtrate. And so all you're doing is you're sitting there, you're counting, you're looking, there's a salt, there's a salt, there's a salt, there's a salt. It's sodium chloride, that's all it's doing. And what happens is when those sodium chloride levels rise, that's going to be a signal to the afferent arteriole to say, hey, you know what? This is a bad thing. You need to slow down the glomerular filtration rate. You're allowing too much salt in because you're pushing it so fast.
So that's how people take out the water.
You can see where this is going. Yes. All right. And then the converse is true as well. When not enough salt is passing by, then what we're going to see is vasodilation. Increase the rate so that we get more filtrate, so we can have more salt passing through. In other words, what we're trying to do is we're monitoring the rate of flow through the tubule by looking at salt levels. And by looking at the salt levels, what we can do is we can determine how fast the filtrate is moving. Because we're going to be removing a certain percentage of salt from the filtrate based on osmolarity. So that's tubuloglomerular feedback. Monitor salt using the macula densa cells. Macula densa cells communicate to the afferent arteriole. Now, the cell that they're working through are the granular cells. You don't need to know that. I'm pretty sure I don't ever ask you a question about that. All right? Now, I don't think I've ever asked a question about coefficient or filtration coefficients, but really what it basically is this is where the physicists or the biophysicists get involved and start, mucking with everybody because they're smarter than everybody else. And really, actually, Dr. Dreyer actually does work with this stuff. And really what it is it basically monitors the degree in which the podocytes, the little foot cells, basically they auto-regulate their size to determine the rate of filtration. So that's actually what we're doing. Deals with surface area and permeability. See? Mostly not understood. Actually, Dr. Dreyer, actually, I think they're in the process of publishing a paper in Nature regarding how this is regulated. Yeah, ooh. Anyone here doing work in Dr. Dreyer lab could probably tell you more than I could. All right, let's make your lives easy. Don't you love it when things are easy? All right. You remember a long time ago I was telling you about the relationship between salt, chlorine, and water? Do you remember that? Or I should say sodium, chlorine, and water. Do you remember that relationship? Sodium and water are like what?
They go together.
Huh? They're that, yeah, well, close. They're the cute couple in high school that everyone hates. Right? You remember that? They're the ones that walk in the halls with their hands in each other's pockets. Wherever one goes, the other one goes. They take the same classes. They sit side by side. They look at each other, do gagaing all the time. And then chlorine, remember, was the friend. You know which friend I'm talking about. The one that follows, hoping that someday sodium and water are going to break up, and then they'll come swooping in and save the day. That's not about right? Do you remember this couple? No? All right. When we're talking about reabsorption, you need to understand that relationship. All right? Wherever sodium goes, water follows. And because they're the popular couple, they have an effect on everybody else. All right? Now, reabsorption is a selective process. Remember, the things that we want to reabsorb are the things that the body wants. The things that the body doesn't want, bye-bye. All right? So, high reabsorptive activity for things that you need, no reabsorptive or little reabsorptive activity for the things you do not need. Now, the filtrate in Bowman's capsule is the same thing as the plasma minus the plasma proteins. Right? So it has the same osmolarity, same salt concentration, sugars, urea, amino acids, you name it. If it's something that is smaller than albumin, which remember we don't know how small it is, but it's small, plasma protein. If it's smaller than that, it's going to be filtered so it looks exactly the same as your plasma. Now, what are you going to reabsorb? No. Whatever you need to reabsorb is going to maintain the composition and volume of your extracellular fluid. That's all there is to it. So, what are we going to do? Well, two processes. We're going to have trans-epithelial transport. That means you move through a cell. Or you have paracellular transport, which means you move in between a cell. All right? One of those two things. We're going to start with sodium. Because sodium is the thing that everyone uses to follow. It's the trend maker. It's the heather. And only 6 or 7 people are going to get that joke. The heather. If you haven't seen the movie, another assignment, The Heathers. Great black comedy. It's hilarious. Anyway, it's about, all right, never mind. It's old, has old people in it now. They're in their 40s. All right, sodium reabsorption is going to be different wherever you are within the tube. All right, so sodium is going to be reabsorbed in the proximal convoluted tubule. It's going to be reabsorbed in the loop of Henle. It's going to be reabsorbed in the distal convoluted tubule. What type of sodium gets absorbed and when it gets absorbed is going to be dependent upon certain needs. 67% of your sodium is going to be reabsorbed in the proximal convoluted tubule. In other words, you can think about it this way. The proximal convoluted tubule plays a major role in reabsorbing materials back into the blood, back into the body. It plays a role in bringing glucose, amino acids, water, chlorine, and urea back into the body. Urea? Yes, urea. Urea is part of our little clique. The loop of Henle, on the other hand, sodium plays a role in creating urine of varying concentrations, as well as volume. I always focus on concentration. The last part, this last little bit, this 8%, is what's going to be reabsorbed in the distal and convoluted tubule and the collecting duct. And it's this that plays a role in extracellular fluid volume. How many of you believe or have been told that high salt diet is bad for you? I mean, isn't that what everyone all says? I mean, aren't they trying to ban salt in New York City? right? The reason that people say sodium is such a big problem is because of this last little bit right here. If I bring salt into my body, reabsorb it into my body, what follows? If I increase my water, what happens? Blood pressure goes up. You see that? All this other stuff plays no role into that. This is the salt that your body wants. This over here is dealing with how do I regulate my osmolarity. It'll make more sense in a minute. Hypotension, you wouldn't be reabsorbing the salt. You'd be getting rid of the water. It's a good question. Now, sodium reabsorption is an active process. Whenever you talk about any type of reabsorption, you have to look along. There's going to be multiple steps. You have to cross at least 2 membranes, and so you're basically looking and saying, how do I get, actually 3 membranes because you have to get back into the blood, how or which of these movements require some sort of energy? If it requires energy, then the process is active. If one step requires energy, it's active. All right? Now, sodium reabsorption requires a sodium-potassium ATPase, right? So if I move sodium into the cell, what do? I'm going to pump it out into the extracellular environment. That's just how my cells are designed, right? That's one of the very first things we learn. Move salt out or move sodium out of cells. And so when you have high concentrations of sodium inside your tubules, they're going to move down their concentration gradients, which is a passive process, and then they're going to be pumped out on the other side. And what you've done is you've basically moved salt. You move salt from the tubule out into the extracellular space. All right? Now, can we take advantage of that? Yes, because we have channels, co-transporters, that allow us to do that, right? We can take glucose into cells, for example. We can take amino acids into cells because of the co-transporters, taking advantage of the high concentration of sodium and moving it into the cell. And then once we've moved glucose and amino acids into the cell, then we can do other things with them. We can have transporters that move them down their concentration gradients and deliver them to where the body needs that glucose or amino acid. And that's what I'm trying to demonstrate here. So when we talk about the reabsorption of glucose and amino acids, what are they doing? They're following Heather, right? They're doing exactly what they're designed to do. Sodium goes this way, well, I'm going to follow. I'm going to go because the machinery allows me to go and use that passive energy, that concentration gradient that sodium has to drive the movement of glucose against its concentration gradient, to drive amino acids against their concentration gradient to get them inside the cells. Once they're inside the cell, all we got to do is take advantage of some sort of channel or other simple diffusion mechanism, to move that back down its gradient. So glucose and amino acids follow sodium. Simple enough? No, it'd be the second step that's active. So let me back up here. Well, so here's step number 1. Here, that would be a channel, passive, right? But now I have low sodium and I'm going into an area of high sodium concentration. So I'm using energy. There's my active step. All right. Over here, what's that? It's secondary active transport, right? So am I requiring energy? No. Where's my energy? It's over here. But it's still, the whole process would be considered active because one step is active. Yeah. There's chlorine. I'm just going to go wherever she goes. Wherever sodium goes, chlorine follows. How fast does chlorine move? As fast as sodium allows it. Chlorine follows sodium. The end. See how easy this is? I can guarantee you're going to have a full lecture of this in medical school and dental school. People are going to be sitting there writing furiously. You're just going to sit there. Sodium, water, everything follows. Right? Yes, sir. It's ionic attraction. That's right. So usually when I give my example, you have to presume sodium or chlorine is following sodium. It's not following water. I know it's weak sauce, but last one is water. Now water, or it's not the last one, it's the second last one. Water is going to be done passively because it's sodium's guide, right? Wherever sodium goes, water is going to follow. Why? Simple osmotic considerations. Where's water going to go and how's it going to do it? Well, it can go through through a cell via aquaporins, or it can pass through paracellularly. All right. Either way, it's going to go wherever there is a lower water concentration, or the more appropriate thing, when there's a higher sodium concentration. So water is going to follow sodium under osmotic considerations. All right. Now, I'm going to point this out here, is that when you pass through an aquaporin, in the proximal convoluted tubule, the aquaporins are always available. In the distal convoluted tubules, aquaporins are going to be dependent upon hormones, right? And which one? Vasopressin. Our good old buddy ADH. Third one, or I think this might be our last one. Yeah. Everyone knows urea is bad, right? Very bad. That's what your body's trying to get rid of nitrogen. Can't stand ammonia, so we convert it into urea, and we get rid of bad. That's right. That's right. It is. And it's also, well, the form of uric acid. It's in the nice, nasty white stuff that the birds put on your car. Here's a little present for you. Thank you. Now, urea is also going to be passively reabsorbed. And what it's doing is it's following water. Again, it's under osmotic considerations. All right. The problem is that it can't move quite as fast as water moves. Sodium moves, water follows, urea follows water. All right. You might think of it as the slow, dim-witted, attracted guy, girl, whatever we're looking at. So what happens is that here we go. Sodium goes, water follows, and then urea moves down its concentration gradient, because when we move water out of the tubule, we're leaving urea behind, so it's becoming more concentrated, and urea out in the body is lower, and so urea is going to want to move down its concentration gradient. But because it moves slower, we end up with a higher concentration left in the filtrate. And so by the time the filtrate leaves, we've gotten rid of excess urea. All right. So what we basically say is that our luminal cell walls are somewhat permeable to urea. Now, in the grand scheme of things, do we know how everything moves in terms of permeability? Wherever sodium goes, water follows. What about chlorine? Follows sodium. What about glucose and amino acids? Follows. And then urea follows water. There you go. Simple enough. You already know the rules why it happens. It's just osmotic consideration. When we come back, what we're going to do is we're going to start with tubular secretion. So enjoy your not long weekend, but enjoy your weekend. When we come back, we'll do this, and then we'll go eat turkey, and then have a good day. Yeah. some sort of arrhythmic attack. This happened previously, so she just had that problem. I'm just going to stop my lecture here real quick, and then I'm going to go out there and wait with her. So, you want to go out there too? No, I'm gonna wrap this up. I'm gonna say my things real quick. They have one EMT out there, who's trained, but that's about it.